Today, we will go through the specification for A3. Then we will go through the skeleton code for A3. So in this assignment, you need to write a C program called mlfq.c, which implements a simulation of round-robin CPU scheduling, which uses we called multi-level feedback queue and a boosting mechanism, which prevents tasks from waiting indefinitely. And there is no threading or synchronization required to complete this assignment. So it will be not very difficult. And you will be implementing a tick-by-tick simulation. And instead of using the actual milliseconds or microseconds, we will just use abstract ticks. So every time we just increment a tick variable, and you will be provided with those files, the makefile and mlfq.c, where you need to write your own code, and you will also be provided with the data structure q.c and q.h. So for these two files, you should not modify them, because we will test your code with exactly the same files. And in these cases directory, you can find some samples. So this is the sample input and this is the sample output, and I will explain later what does this means. Okay, so let's go back to the assignment. So first, let's take a look at the specification for multi-level feedback queue. Okay, so the multi-feedback queue is designed to ensure that tasks require quick responses are scheduled before tasks which are more compute bound, which means that those tasks are having longer CPU bursts. So your simulation will be of an MLFQ with 3 different queues. So Q1 with a quantum of 2, Q2 with a quantum of 4, and Q3 with a quantum of 8. And when a new task arrives, it is enqueued onto Q1. And when there is a CPU scheduling event, Q1 is examined. If it is not empty, then this task at the front of the queue is selected to run and given a quantum of 2. Otherwise, we will examine Q2 and Q3. And if a task selected from either Q1 or Q2 finish its current burst within the quantum provided to it, it will be placed at the back of the queue from which it was taken. However, if a task selected from either Q1 or Q2 has a burst that exceeds its quantum, then it is interrupted and will be placed into the next queue with a larger quantum. So, which means that if a task taken from Q1 would be placed at the end of Q2, and a task taken from Q2 would be placed at the end of Q3. And if the scheduler discovers that there is a task on a higher priority queue than the current task, the currently running task will be preempted. And without any mechanism which allows processes to leave Q3, a process may have to wait indefinitely. So we will use a mechanism called boost that occasionally to take the task from Q3 or Q2 to Q1. So later, the mechanism about boost mechanism will be provided. Okay, so first let's look at the input and output of the MLFQ simulator. So to run the test case, you can follow the exactly the same command. So this will take the test 1 as the input to MLFQ. So let's first look at test1.txt. So the first line is 1, 1, 0. The first one means the first column means the current tick. So at tick 1, the task with ID 1 is created. 0 means created. And at tick 2, the task with ID 1 will generate a CPU demand for 17. So let's go back to this assignment. So each line of the simulation case text file represents one of 3 possibilities: task creation, task requires CPU time, and task termination request. So for example, a line such as 1330 indicates that at tick 13, task 3 has been created. 0 means creation. And a line such as 1436 indicates that at tick 14, task 3 initiates an action that will require 6 ticks of CPU time. And lastly, a line such as 21, 3, -1, which means at tick 21, the task with ID 3 will terminate once its remaining CPU burst ticks are scheduled. If no such ticks, then the task would terminate immediately. Okay. Now let's look at the example of the input and output. So at tick 1, the task 1 is created. So you can see the output here. This is the tick 1, and this is the ID 0001, and new means that this task with ID 1 is created. And here we also have a output of idle, because at tick 1 there is no scheduling, because the task just be created and has no action of any requirement for CPU ticks. Into tick 2, task 1 initiates an action that requires 17 CPU ticks. So we can see that at tick 2, the task with ID 1 requires 17, and used 1 means that the current tick also counts for one of those 17 ticks. So used 1, and initially this task will be enqueued into Q1, and at tick 3, this task used 2, and it is still in Q1. However, by the end of this tick, we know that Q1 only has 2 CPU quantum, and this task has already used 2. So at next tick, this task will be enqueued into Q2. and into tick 7, because tick 7 there is a new task with ID 2 is created. However, when this task is created, this task does not initiate any actions at tick 7. So at tick 7, we can still process the task 1. And by the end of this tick, we can see that task 1 has already used 4 CPU quantum, 1, 2, 3, 4. So from so this task will be included into Q3. And then we can see that at tick 8, task 2 has initiated an action that requires 1 CPU time. So at tick 8, task 2 requires 1, used 1, and it uses the Q1. And we can see that there's no events in tick 9, tick 10, tick 11, and tick 12. So in the following ticks, because there are still remaining CPU bursts for task 1, so at tick 9, we will schedule the tick for task 1. So you can see that from 9, the Q for task 1 is 3, because it has already used the CPU quantum for Q1 and Q2. And into Q3, into tick 13, task 3 has been created. And at tick 14, task 3 will initiate an action that requires 6 CPU ticks. So at tick 13, we can still process task 1. And at tick 14, because task 3 is newly created, so it will be put into Q1. So we will interrupt the current processing task for task 1 and process task 3. So task 3 will initiate an action that requires 6 CPU ticks. So we can see that it will process the CPU ticks in Q1 with 2 quantum, and then put into Q2 for 4 quantum. However, because at tick 18, task 2 initiate an action again with a CPU burst 1. So the CPU scheduler will interrupt the processing for task 3 and process task 2 instead, because the requirement is only 1 CPU tick. So at the next tick, we can process task 3 again. Okay, so at tick 21, task 3 initiate a termination process, and because that there is no CPU bursts left, so task 3 will exit, and with 2 statistics. The first is waiting time. The waiting time is 1, because we can see that in this process, at tick 18, task 3 wait for task 2 to be completed, and it only wait for 1 tick, so the waiting time is 1, and this is turnaround time, which means the total time for its processing and for waiting in the queue, so which is 7, because the time for processing it takes 6 CPU ticks, and the waiting time takes 1 CPU tick, so the total turnaround time is 7. And then we can process task 1 again. In queue 24, tick 24, task 2 initiate an action for 1 CPU tick, and it will interrupt for processing task 2. And at 25, tick 25, task 2 initiate a termination process because there is no CPU burst left. So task 2 will exit with waiting time 0 and turnaround time 3. And at tick 25, we have a boost process. So in this assignment, every 25 ticks, we will call the boost procedure. So in this boost procedure, we will put the task 1 from the queue 3 to queue 1 and continue to process it. In queue 28, we can see that task 1 has finished all the CPU bursts and wait and exit with the waiting time 9 and turnaround time 26. And at tick 28, there is no task being processed, so CPU is at idle. Okay. So I have already mentioned in this example, we have some task metrics. So this is for the requirement for 6 ticks, and we have used 2 ticks, and this is the queue ID. And when a task exits, we have a waiting time 1 and turnaround time 7. So the waiting time is the how many ticks that the task spent waiting in this MLF queue, and the turnaround time is the sum of the ticks for which the process was scheduled, the CPU, plus the ticks for which it was waiting on this queue. So in order to keep track of the total number of CPU ticks, you need to correctly increment the field called total execution time and task T. So this has been defined in this data structure. Okay, now let's take a few words for the boosting process. The program must prevent the task from being stuffed for CPU time. So every 25 seconds, which means on tick 25, tick 50, and tick 75, we need to call this boost function. And this boost function will move all tasks from the bottom queue, Q3, to the top queue, Q1, and then move all the tasks from the middle queue, which is Q2, to the top queue, which is Q1. Okay, let's then go through this code. So first, let's go through the data structure. So we have a structure called task. In this task, we have the ID for the task ID and the burst time for the action that for record the burst time for any action initiated by this task, and the remaining burst time, which means how many burst time that has not been scheduled, and current queue, which stores the ID for the queues where the task is in queued, and this is total wait time. So every time if task is not scheduled and is waiting in the queue, this field will be incremented by 1, and this total execution time is also for computing the turnaround time. So every time if this task is scheduled, this field is incremented by 1, and this is the queue for this is the pointer for the next task. And we also have an instruction. The instruction is to store the instruction from the input file. So this is the event tick, task ID, and burst time. And this records whether we have finished reading all the instructions from the sample file. And we have a queue. So in this queue, we just store this task structure. So this is an eclipse. And we have function initial queue and check whether the queue is empty, and in queue, and dequeue and deallocate. So let's now come back to this file. So in this file, we first have some constants. So max input line is 100, which means we will not have more than 100 instructions. And the max task is 10. So we will not have more than 10 tasks. And the boost interval is 25, which means at tick 25, tick 50, and tick 75, we will initiate a boost procedure, moving all the tasks from the bottom queue to the top queue, and then from the middle queue to the top queue. And this is the queue time quantums. So the top queue has two CPU quantum, and the middle queue has 4 CPU quantum, and the bottom queue has 8 CPU quantum. And we will initiate 3 queues, Q1, Q2, and Q3. And we will create an array of task table. Okay, so in this array, we have max tasks, which is 10, and create a pointer to the current task. And this is the remaining quantum for the current task. Okay, so let's go to the main function. Okay, so in the main function, we first create the tick equals to 1. So we start the simulation start from tick 1, and this is instruction complete. Okay, this is the flag to check whether the instruction is complete or not. And we check the arguments input when we run this program is valid or not, as we want to give the file give it the file in the instruction file to this function. So we want to validate. And we will initialize some variables. So let's take a look at okay. So in this function, we just initiate queue, 3 queues, and then we open the file, the instruction file, and check whether the file has opened or not. And next, we initiate, we allocate a memory space for the instruction T and read the first instruction. So let's take a look at this function, read instruction. So in this instruction, so this function will read a single line from the input file and stores the appropriate values in the instruction pointer provided. So in case of EOF is encountered, the EOF flag is set. Okay, so every time it will read this instruction from this file. Every time call this function, it will read a line from this file. So this is for the read instruction. So it first read an instruction from this file and check whether the current instruction is EOF, and if it is not, we can handle this instruction by using the handle instruction. So this function is what you need to write, and you need to process the input instruction depending on the type, like whether it is a new task. So the new task, the burst time will be equal to 0, and whether task completion. So you need to check what the burst time, whether it is -1. If it is -1, you need to schedule some termination process, and it can be a task burst. So the burst time will be read from the file. Okay, and in this function, you will perform no task scheduling, no preemption, and no updation, because this task would be handled by the scheduler function. And if a task once demoted to a level, retains that level for all future bursts, unless it is further demoted or boosted. Okay. So you can see here, if an instruction burst time is equal to 0, which means there is a new task arrived. So when a new task arrives, you need to just register it, like into the task table. And if the task is -1, we need to do some termination process. For example, we need to calculate the waiting time and turnaround time, and if we can terminate it, we will print the things into the file, into the terminal. And else, if there is a CPU burst for the task, we need to include this task into the queues. And then we will read the next instruction and check whether we need to have a boost procedure. So in this function boost, we need to check check whether current term interval is equal to 25, 50, 75, and so on. And if so, we will move all the tasks from Q3 to Q1 and from Q2 to Q1. So this is the boost process. Next, how to handle the scheduler is in the function scheduler. So in this scheduler, what you need to do is to dequeue the task from one of the queues. Okay, if there is a queue, if there is a task with higher priority than the current running tasks, you need to preempt the current task by the high priority task, and the preempted task is included to the end of its associated queues, which is the queues where it was taken from. And then we need to update task metrics. So in this update task metrics, for those tasks that are not scheduled, we will increase its waiting time if they are in the queue. And if a task that is scheduled, we will increase the execution time for this task. So this function is used to update task metrics. And here we will execute task. So in this function, execute task will just increment the execute task will just executes the current task, just update the associated remaining times, and set the current task to null if the current burst is complete. Okay. Okay, then at last we just increase the tick. Okay, so this is all for today's video, and if you have any question, just feel free to ask.